Hello, welcome to a new video on complete metric spaces. In this video we are going to define Cauchy sequences first. Using this definition we will define complete metric spaces. First of all, let's see what's a Cauchy sequence. So let's consider a metric space X together with a metric D. That means D defines a distance. D attaches the notion of distance with that metric space, and we take a sequence xn which contains members x1, x2, etc., x1, x2, x3, etc., up to x infinity. See the point at infinity. The point or at the position, x infinity is the member of the sequence at the infinite position. See, it is not the point at infinity. Okay, and then the sequence, it is shortly written as xn. N varies from 1 up to infinity of points of x, but this sequence contains only the points of x. It takes only the points of x, the metric space x. We say that it's a Cauchy sequence. We can say that it's a Cauchy sequence. This sequence is a Cauchy sequence if for every epsilon chosen, see, we are choosing an epsilon, and this quantity epsilon has the property that it is positive. It must be a positive quantity, a positive real number. For every for any positive real number epsilon chosen, but normally it has an additional property that it tends to 0. See, when we consider a quantity for epsilon, and we will in the next stage we will consider a smaller quantity for epsilon which is also positive, so epsilon must be tending to 0. When we verify this property, this condition for a quantity of epsilon, then in the next verification, if you continue that verification, it must be verified for a smaller quantity of epsilon. So that's why we consider that we say that epsilon is tending to 0. So epsilon tends to 0. Epsilon is a real number which is tending to 0, and then corresponding to each epsilon there must exist an integer n. So we can more clearly we can say that it is indexed by the value of epsilon. So n epsilon you can write, but since this that information is clear here, or since the number n is related to epsilon, that information is clear, we just say that it is n. There exists n, an integer n, and two more integers there exists related to this, m and n, such that these quantities, these integers m and n, are greater than or equal to n. So there exists a limit, a lower limit for this integer, for the existence of two integers m and n, such that the distance between xm and xn and xm, or xm and xn, is less than epsilon. So what does it mean? It means that you measure the distance from the point from the element at the nth position in the sequence to the element at the mth, which is at the mth position in the sequence, then that distance will be less than the selected quantity epsilon. So this must be true for every choice of epsilon. For every quantity chosen for epsilon, this must be true. That means there must exist an integer n, and that integer must satisfy the condition that any m and n whose value, any two integers m and n whose value greater than or equal to n, the distance between them must be less than epsilon. See, this kind of if there is a sequence satisfying this condition, we say that it's a Cauchy sequence. The quantity is epsilon. See, the quantity chosen epsilon and the integer n, then higher two additional integers m and n, all these together make a system, and that system actually determines the distance between the two elements in the sequence, and verifies that whether it is less than the quantity and less than the chosen quantity epsilon. Okay, once after defining this the Cauchy sequence, um, let's think about the convergence of the sequence. After when we think or study about the sequences, the important question that comes to our mind is that whether there exists a point or a value to which that sequence converges, and that point is called the limit of that sequence. So you might have studied that you have that idea of limit of a sequence. So in this case also, after defining the Cauchy sequence, you can think that whether there exists a limit for that sequence. But moreover, here we think about the existence of the limit of the sequence, considering or in the background of the existence of the space in which that sequence exists. So actually we are choosing that Cauchy sequence. We are choosing a Cauchy sequence from a metric space or a subspace of that of a metric space. So from we are choosing it from a space, a metric space. So the question is now whether the limit of that sequence exists and whether it is present in that in the metric space in which actually that Cauchy sequence belongs. So that idea is now is explained here, or we are going to define a concept related to this idea. Every Cauchy sequence may not converge to. Before coming to that concept, actually we are going to define a complete metric space, a property of a metric space that is related to the convergence of a Cauchy sequence in that to a point in that metric space. But before that, we have to say that every Cauchy sequence may not converge to a point in the metric space in which actually that sequence is present, or from the metric space it is actually chosen, selected. So but a metric space having the property that every Cauchy sequence converges to a point in that metric space, and that kind of metric space is called a complete metric space. So we can formally define a complete metric space. A metric space XD is a complete metric space if every Cauchy sequence selected from or that exists in that metric space, every Cauchy sequence which exists in that metric space, if that Cauchy sequence converges to a point that point is also present in that metric space, or if it converges to a point in that metric space, then we say that that metric space is complete. So you just suppose that a metric space contains one Cauchy sequence. If it contains one Cauchy sequence which does not converge to a point in that metric space, but all the other Cauchy sequences which exist in the metric space converges to some point in the same metric space, so then in that situation also the metric space is not complete, because there exists an exception. There exists one Cauchy sequence which does not converge to a point in the metric space. So for a metric space to be called a complete metric space, what is the essential thing? Every Cauchy sequence must converge to a point in that in that space. Every Cauchy sequence must converge into a point in that space. Then only we can say that space is a complete metric space. Okay, and therefore this is very important. That word, that every, that is very important. See, in some metric spaces, some Cauchy sequences may be converged to a point in that metric space, in the metric space, but that does not say that does not ensure that the metric space is complete. See, we have a theorem. First theorem here that we have to discuss is that tells us about the complete metric space, and then subspace, a complete metric space and subspace of a complete metric space. Okay, what does it say? Let XD be a complete metric space. Here we consider a complete metric space x comma x together with a metric D. Let it be a complete metric space. It is given that it's a complete metric space, and then we think about a subspace. We consider a subspace of that metric space. Of the complete metric space, a subspace, we choose a subspace of the complete metric space. Let A be a subspace of the complete metric space. See that metric space, that subspace will be complete if and only if, see, that space is complete, that subspace is complete if and only if it is closed. So theorem states that. So it links with the property of closed subspaces, or closeness of the closeness property of the subspace with the completeness property. See, the two properties are now here linked. Actually, completeness is supported by closeness, and closeness is supported by completeness, and that is the essence of this result. So how can we prove this? So one way you have to show that, you have to assume that the space XD is the space X is complete, and then you have to show that by choosing, after choosing a subspace, we have to you have to show that a subspace which that's also complete. That I see throughout this throughout the proof of the result, X is a complete metric space. X stands as a complete metric space, and then you have to start with a subspace. First we start with a subspace A which is complete. If it is complete, then you can show that it is then closed. And then to prove the reverse part, you can assume that a subspace A is closed, and then you have to show that it is complete. If a subspace A is closed, then you have to show that it is a complete it's a complete subspace or a complete metric space. So for the, let's begin the proof. Suppose that A is a complete subspace, so XD is a complete, the space XD is complete, and we then take a subspace A. Suppose A is a subspace, and that's complete also. We assume that A is complete. Let A be a subspace, a complete subspace of XD. And what we want to show now, we want to show that A is then closed. We want to show that A is closed. See, how can we show that A is closed? For that we will show that A contains all its limit points. The property of closed that we use here. What is the property of closed set? We say that in a metric space is a subset is closed if it contains all its limit points. So we want to show that A contains all its limit points. Okay, A contains. We want to show that. We are going to show that A contains all its limit points. So let's choose if you want to show that A contains all its limit points, you have to choose at least one limit point of A. Okay, we will pick one limit point of A. A limit point of A we will choose, and we will call it X, and then we will show that X then belongs to, if it's an arbitrarily chosen limit point, then all limit points will be belonging to A. After once we show that X belongs to A, so let's choose an arbitrarily limit point of let's choose an arbitrary limit point of A, or we choose arbitrarily a limit point of A, and we call it X. X is a limit point of A that's chosen arbitrarily. Okay, then we know that there is a sequence. Since X is a limit point of A, see, when X is a limit point of A, we can apply that the definition of a limit point. What does it say? Then there is a sequence. There exists a sequence in A. Then definitely we can find a sequence in A which converges to X, because X is a limit point of A. There exists a sequence in A which converges to X. Okay, but you know that since that sequence, see, that sequence is not written here as xn, the sequence xn. Yeah, of course you can think that this is that sequence. So this sequence xn, that is a sequence in A which exists in A that converges to X. But since A is a subset of the space X, since A is a subset of the space X, and the same sequence is present in X also. So see, we can say that the same sequence, whatever sequence here exists, that sequence is present in the space, in the entire space. And but we also know that that entire space is complete. So this sequence is present in this sequence is that exists, that converges to X also, that converges to X. So the sequence Xn converges to X, and that is present in the complete metric space X. We know that X is a complete metric space. Throughout the proof of the result, we know that X is a complete metric. X stands as a complete metric space. But you know, this sequence converges to X. Since you should also remember that every convergent sequence is a Cauchy sequence. See, since every convergent sequence is a Cauchy sequence, here this sequence, the sequence here which exists here also is a Cauchy sequence. So this is a Cauchy sequence. Thus we have a sequence which converges to X, that's a Cauchy sequence, and this Cauchy sequence is a member of the space X, a complete metric space X. What does it say then? Then we can say that this Cauchy sequence, since it's a member of the a complete metric space, and then that is present in that limit is its limit is present in X. Thus, since X is complete, since the space X is complete, we can say that the Cauchy sequence, which is now the sequence Xn, which is now it's known as a Cauchy sequence. This sequence converges to a point in X, and that means the limit of the sequence X is a member of X. So X is present in this small x is present in the space X. Okay. And you know, but you know, the Cauchy sequence is the and then the sequence is a Cauchy sequence. Okay, and A is then complete. Then and A is complete. You know that it's we also know that we have assumed that. You know, X is also complete, and moreover we have assumed that what does we assume here, and the space A is a complete. We have in the beginning we have started assume that the A is a subset, and also it's a complete subspace. Yeah, it's a complete subspace. Since A is a complete subspace, so we also know that A is also a complete subspace. Thus, you know, it's a Cauchy sequence, and also it converges to X in X. Moreover, it converges to, since A itself, the subspace. See, as a subspace, A itself is a complete subspace. Since A is complete, since the space A is complete, we can say that the sequence Xn converges to the point X. Okay, and that converges to a point in A also. Okay, so that how does it follow? It's because the sequence A is we know that the sequence A is also complete. In the beginning, we have assumed that the subspace A is complete. So due to this, the sequence which converges to X, it converges to a point in the subspace, and that point is nothing but the point small x. Okay, and that means that. So what does it say? It says that the point X, that's the limit of the sequence X, is present in A, and thus the sequence Xn is it's convergent to it converges to a point X which is present in A. But finally we can say that we can conclude that the point X is present in A, and therefore A is present in X. The point X is present in A, and that is A is closed. Actually, to get that A is closed, we wanted to show that the point X, that is the limit of it's a limit point of A. X was actually taken as a limit point of the set A. and then after that we have taken a sequence, and then we showed that we stated that, or we showed that, or we argued that it's a Cauchy sequence, and then that Cauchy sequence helped us to show that the point x is in A, x belongs to A, because the set A is the subset A is complete, and therefore we get that x is present in A. So whichever limit point of A that we choose, you can say that limit point is a member of the subspace A, and that means A is closed, the space A is closed. Next, to prove the convex part, conversely we assume that A is a closed subspace. Let's assume that A is a closed subspace of a complete metric space X. See, we take A as a closed subspace of a complete metric space X, and we want to show that A is complete. Then we want to show that the space A, the subspace is that closed subspace A is a complete complete subspace. We want to show that A is complete. How can we show that? Show this? For that we have to consider a Cauchy sequence for every for this we can we have to choose arbitrarily a Cauchy sequence. And then we want to show that it converges to a point in that subspace which belongs to that subspace. The limit point which belongs to the subspace converges to that a point in that subspace. So we choose arbitrarily a Cauchy sequence, and that sequence is xn, where n varies from 1 to infinity. And also see, it contains only the points of A, so that means it's a subset of this sequence. This Cauchy sequence is a subset of A. Since x is you know that x is complete. Since x is complete, and this sequence since it's a Cauchy sequence, since x is complete, this sequence converges to a point. It must converge to a point. Say that point is x, small x in x. So it converges to a point small x in x. Since A is closed, okay. Since A is closed, now the fact that A is closed can be used. Since A is closed, then this limit, actually this is the limit of that sequence. X, small x, is the limit of the sequence. Since A is closed, and x is the limit of the sequence, then x must belong to A. X belongs to A, and thus each Cauchy sequence, see, since x belongs to A, we can say that since xn is the Cauchy sequence chosen from the subspace A, every Cauchy sequence, see, we can say that and also it's an arbitrarily chosen Cauchy sequence, then we can say that every Cauchy sequence which belongs to A converges to a point in which is present in that point. Also the limit is also present in A. Thus every Cauchy sequence converges to every Cauchy sequence which belongs to A converges to a point in A. Hence A is a complete subspace. Therefore the subspace A is complete, and thus it is a complete subspace. And that's the end of the proof. Okay. Next we want to make a comment on the topological equivalence and the property of completeness. See, you should note that the property of completeness is not a topological property. What's meant by a topological property? A topological property is a property that is transferred from one topological space to another topological space by a continuous function. See. And so here by saying that completeness is not a topological property, we mean that there can exist two topological spaces that are topologically equivalent. So there can exist two topological spaces that are topologically equivalent, but one space can be a complete, but the other space, the second space, may not be complete. So being complete, one space, the same time one space can be complete, but the other space may not be complete. See the example. For example, the real line, you know that the real line R and the open interval 0 1 are topologically equivalent. We have proved that the real line R and the open interval 0 1 are topologically equivalent. But you know, the open interval 0 1 is not complete, but the real line R is complete. We can prove that the real line R is a complete space, complete metric space, but the open interval 0 1 is not a complete metric space, because you can consider the sequence 1 by n. See, that's a Cauchy sequence. The sequence 1 by n, xn equal to 1 by n. It's a Cauchy sequence. You can easily show that it's a Cauchy sequence. It converges also. It converges to the point 0. 0 is the limit of that sequence. It converges. Of course, it converges. The Cauchy sequence converges, but it does not converge to a point in this subspace, and that's the problem. And that it's a Cauchy sequence. It does not converge to a point because its limit is 0. But 0 is not present in this subspace because it's an open interval. 0 1 is an open interval, so 0 is not present in this subspace. So it does not converge to a point in this space. So that's why we see that, or I suggested, I commented that the convergence of Cauchy sequence actually depends on that the space in which that Cauchy sequence is present. We have to say that we have to comment, or we have to mention about the convergence, and it's the existence of its limit only based on the space in which that Cauchy sequence is actually present. Okay, that's an important thing. So once again we can say that the property of completeness property is not a topological property. That means two spaces can be topologically equivalent, but one space can be complete. When one space is complete, the other space cannot be complete. Yes, this is a very good example. The spaces R and the open interval 0 1 are very good examples for the two equivalent spaces which are one is complete but the other is not complete. Okay, thank you.